Welcome to the Deep Dive. Today we're looking at something pretty extraordinary, where AI meets scientific discovery.
Yeah, it's fascinating stuff.
Imagine a system, right, that doesn't just write code, but it actually evolves it autonomously to solve problems that have stumped people for, well, sometimes decades.
Exactly. We're talking about AlphaEvolve from Google DeepMind, and it's more than just, another LLM application. It really feels like a different way to tackle these super hard computational problems.
We're basing this discussion on the white paper, AlphaEvolve, a coding agent for scientific and algorithmic discovery.
That's right, by Novikov and the team.
So our mission today is to unpack how this thing works, its autonomous pipeline, look at some of the really impactful applications, and get into the technical innovations that let it push these boundaries.
Yeah, get ready for a proper technical look. This agent is literally rewriting algorithms.
Okay, so let's start with the basics. What is AlphaEvolve, fundamentally?
At its core, it's an evolutionary coding agent. It manages this whole autonomous process using large language models, LLMs.
Okay.
And its main job is to take an existing algorithm and make it better by directly changing the code.
How does it know if it's getting better?
Through a continuous feedback loop. It makes a change, gets evaluated, learns from that, and tries again. It's this iterative improvement cycle.
Driven by automated evaluation.
Exactly. That's key. It works best on problems where you can automatically check if a solution is good or not. Think math, computer science, optimizing systems. This machine-grade ability is fundamental.
Right. Now, how does this compare to earlier systems? FunSearch comes to mind. What's the leap forward here?
Yeah, good question. It's a significant step up in ambition, really. FunSearch typically worked on, say, single functions, maybe 10, 20 lines of code. AlphaEvolve tackles entire code files. We're talking hundreds of lines.
Wow, okay. Big difference.
Huge. And it's language agnostic, not just Python. Plus, it can handle much longer evaluation times hours using parallel processing on accelerators.
Whereas FunSearch needed really quick evaluations, right? Like on a single CPU.
Precisely. Less than 20 minutes, typically. AlphaEvolve's ability to use heavy-duty evaluation unlocks different, more complex problems.
And interestingly, it's apparently more sample efficient. It needs fewer LLM attempts.
Yes, significantly fewer. Thousands of samples compared to potentially millions before.
How does it manage that?
Well, a couple of things. It uses state-of-the-art LLMs, specifically in Ensemble, combining Gemini Flash for speed and Gemini Pro for, let's say, deeper insights.
An ensemble approach. Makes sense.
And crucially, it feeds these LLMs much richer context and feedback in the prompts. It's not just asking blind questions, it's providing a lot of information to guide the generation.
And it optimizes multiple things at once.
Correct. Multi-objective optimization. And that's interesting because sometimes, even if you only care about one metric, optimizing for several can actually lead to a better result for that single target.
How so?
It encourages more diverse solutions, helps it avoid getting stuck in a rut, a local optimum that a single-minded approach might fall into.
Okay, fascinating. So let's walk through how it actually operates. It starts with the user, right?
Yes. The user defines the what. They set the evaluation criteria, provide a starting program.
Maybe some background info too.
Optionally, yes. And critically, they mark the specific code blocks they want AlphaEvolve to work on. They use special comments like #evolve block start.
So you can just point it at a piece of a larger existing project.
Exactly. Makes it really practical. Then the user provides the evaluate function, usually Python, which returns the scores, the metrics.
And that kicks off the main loop.
But kicks off the evolutionary loop. Yeah. It's managed by a distributed controller.
Okay.
There's a prompt sampler that picks programs to work on from a program database. This database holds all the past attempts, ideas, and how well they scored.
Is that database just a simple list?
Oh no, it's quite sophisticated. It uses ideas from things like MAP, Ellipse, and island models. The goal is to cleverly balance exploring brand new ideas, exploration, with really digging into the promising areas it's already found, exploitation.
Got it. So the sampler picks a program, feeds it to the LLMs.
Right, the LLM Ensemble, Gemini Flash, and Pro. They get these rich prompts full of context.
And the LLMs then suggest changes.
They generate code modifications, often as diffs, in that standard search replace format. Or for shorter bits, maybe a complete rewrite.
And these modified programs then get tested.
Yep, sent off to the evaluators. They run the code using the user's evaluate function, get the scores back, maybe some other feedback too.
And the good ones go back into the database.
Exactly. Promising solutions, their scores, everything gets registered back into the program database. And that feeds the next cycle of sampling and improvement.
You mentioned the evaluation itself is advanced. What does that involve?
Well, there's this evaluation cascade. New ideas get tested first on easy cases. Only the ones that pass move on to harder tests. It prunes weak ideas early, saves compute.
Smart. Efficient.
Very. And what's really novel is that LLMs themselves can provide feedback. Not just numerical scores, but maybe subjective things like, is this code simpler? And that can influence the evolution too.
So AI evaluating things like code elegance, potentially?
Sort of, yeah.
Yeah.
Beyond just performance metrics. And of course, it's all massively parallelized. Evaluations happen concurrently across distributed clusters to get through lots of ideas quickly.
Okay, that's mechanics. Let's talk impact. What does this actually achieve? Some big claims in the paper. Matrix multiplication, for instance.
Well, absolutely. This is where it gets really impressive. AlphaEvolve improved the state of the art for, I believe, 14 different matrix multiplication scenarios scenarios.
14.
Yeah, but the headline result is for 4x4 complex valued matrices. It found an algorithm using 48 scalar multiplications.
And the previous best was?
49 using Strassen's method, which has been the benchmark for 56 years.
56 years. That's incredible. The first improvement in over half a century.
That's right. And it wasn't just finding the algorithm. AlphaEvolve actually modified the search process itself to get there, adding things like gradient noise, special annealing techniques, really sophisticated meta-optimization.
Wow. Okay, beyond matrix multiplication, it tackled open math problems too.
It did. Over 50 problems across different areas, analysis, combinatorics, number theory.
And the results?
Matched the best-known solutions in about 3/4 of the cases, and actually beat the state-of-the-art in around 20%.
That's significant. Any specific examples that stand out?
Yeah, a couple are really notable. It improved the lower bound for the kissing number problem in 11 dimensions, bumped it from 592 to 593.
Which might sound small, but those bounds are notoriously hard to push.
Extremely hard. And it also found a new upper bound for Urdu's minimum overlap problem.
How did it approach these? Was it directly finding the mathematical objects?
Interestingly, no. The key innovation there was evolving heuristic search algorithms, giving them a fixed time budget and letting AlphaEvolve discover better strategies for finding good constructions rather than finding the constructions directly.
So it's learning how to search effectively. That's meta-discovery again.
Exactly. Autonomous discovery of adaptive search strategies. Very powerful.
Now, shifting gears slightly, what about real-world applications inside Google? Data center scheduling.
Yes, this is huge practical impact. It found a surprisingly simple but very effective heuristic function for Google's Borg system. That's their massive cluster manager.
And the effect?
This heuristic recovers, on average, about 0.7% of Google's entire compute fleet resources that would otherwise be wasted or stranded.
0.7% of Google scale compute? That's enormous.
It's a massive amount of resource saving. And critically, compared to maybe a complex deep RL solution, this heuristic is interpretable, easy to debug, predictable, all vital for a mission-critical system like Borg.
Makes sense. What about optimizing AI training itself, like for Gemini?
Also, yes. It optimized tiling heuristics for critical matrix multiplication kernels. These are core operations used when training huge models like Gemini.
And the speed up.
An average of 23% faster for those specific kernels, which translated to about a 1% reduction in the total training time for Gemini.
Again, at that scale, 1% is significant.
Absolutely. And it also slashed the time needed to optimize these kernels from months of human engineering down to just days using AlphaEvolve.
And there's a kind of recursive element there, right?
Yeah.
Gemini optimizing its own training via AlphaEvolve.
Precisely. A really interesting self-improvement loop starting to form.
It even touched hardware design. TPUs.
It did. It took a highly optimized Verilog implementation. That's the language hardware designers use for a key arithmetic circuit in Google's TPUs.
Yep.
Found a simple code change, removed some unnecessary bits, reduced chip area and power consumption. And this was validated by the actual TPU designers.
So AI directly contributing to hardware design improvements
Yeah.
in the language engineers use.
Yeah, Gemini's first direct contribution to TPU circuits, apparently. A glimpse into AI-assisted hardware design.
One more application optimizing compiler output, like flash attention.
Right, this was a really tough challenge. They pointed AlphaEvolve at the XLA-generated intermediate representation, the IR, for the flash attention kernel.
That's pretty low-level stuff, usually heavily optimized already.
Exactly. It's compiler output, often just for debugging, not really meant for direct editing. But AlphaEvolve managed a 32% speed up for the main flash attention kernel.
32%, on top of compiler optimization.
Yes. And a 15% speed up in the surrounding pre- and post-processing code, too. It shows AlphaEvolve can find optimizations even in code that's already been through sophisticated compiler passes.
Which hints at maybe integrating this kind of thing into future compilers.
Potentially, yeah. Or as a post-compilation optimization step. Very interesting possibilities there.
Okay, so with all these components, the evolutionary approach, the rich prompts, the LLM ensemble, full file editing, how do we know what's actually making the difference? Do they test the parts?
They did. They ran rigorous ablation studies, basically turning off different components one by one to see the impact on performance.
Yeah, and the outcome.
The results were clear. Every major piece contributes significantly. The evolutionary framework, the quality of the prompts, using meta prompts, evolving whole files, using those powerful Gemini models, removing any one of them hurt performance.
So it's not just one trick, it's the whole system working together.
Definitely. It's a synergistic system. The combination is key.
So let's wrap this up. We've seen AlphaEvolve combining these powerful LLMs with evolutionary methods and really precise automated feedback.
Right.
And it's not just spitting out code, it's achieving verifiable scientific breakthroughs, like that matrix multiplication result, and delivering real measurable value in complex systems at Google.
It really bridges that gap between AI potential and tangible high-value results.
And here's a thought to leave you with. You mentioned AlphaEvolve is optimizing parts of its own infrastructure, including the LLMs like Gemini that power it.
Yeah, that recursive self-improvement loop.
What does that mean long term? When AI systems can systematically, autonomously improve the very algorithms and even the hardware they run on, what happens to the pace of scientific progress then?
It's a profound question. And are there whole classes of problems, maybe ones we can't easily automatically evaluate today, that might become solvable as these AI systems get smarter about problem solving itself?
It definitely highlights the incredible potential sitting at this intersection of AI and automated discovery. Something for all of us, maybe in our own fields, to think about where could these advanced coding agents unlock the next wave of breakthroughs.